So Marco Abbadini is going to tell us about the doctrinal Herbrand's theorem and its stone dual.
Okay, imagine going back to the place where you learned a certain dialect and meeting your former teachers, your former colleagues, and being able to speak that dialect together. And that's great, and that's how I feel today. So I feel honored to have the opportunity to speak at this at the place where I grew up as a practitioner of this dialect that we call mathematics. And for this I thank the organizing and the program committee. And one of these former colleagues is Francesca Guffanti, and I'm happy to present today a joint work with her. And working with her, for me, it's an amazing experience because, well, we can combine our expertise and her expertise on doctrines with mine on stone duality, which are two of the three ingredients in my talk. So let's see quickly these three ingredients: doctrines, Herbrand's theorem, and stone duality. Herbrand's theorem describes the validity of an existential formula, so the form exists x phi of x with phi quantifier free, in terms of the validity of certain quantifier free formulas. So in a certain sense, it eliminates the existential. So in terms of the validity of quantifier free formulas, so one can prove exists x phi of x if and only if there are term definable constants C1, Cn, such that the disjunction of all these phi psi I, Ci is provable. This in general holds modulo any universal theory T. So any theory made up of universal closures of quantifier free formulas, such as the theory of preorders, or if you have the equality, the theory of partial orders, any quasi-variety of algebras. If from the theory you can prove exists x phi of x, then you know that to prove it, there must exist a finite list of weaknesses. Okay, this is Herbrand's theorem, the first ingredient. Second ingredient, first order Boolean doctrines. Well, just like Boolean algebras are the algebras of classical propositional logic, first order Boolean doctrines are the algebras of first order classical logic. Going back to Lawvere. Third ingredient is stone duality. Now, classical stone duality is a duality between Boolean algebras and stone spaces. So between the algebras of classical propositional logic, Boolean algebras, and the spaces of models of classical propositional logic, which is stone spaces. But there is also a corresponding version in the first order case. In this case, the algebras are first order Boolean doctrines, and the spaces of models in the usual first order sense are polyadic spaces. And so now I can state the aims of our work. First, I will quickly address the question, what is the reading of Herbrand's theorem in terms of doctrines, so in terms of algebras of formulas. And then I will turn to what is for me the fun part. So what is the stone dual of this Herbrand theorem? So what does it tell us in terms of spaces of models? Let's see quickly the doctrinal reading of Herbrand's theorem. For this, I have to recall what is a first order Boolean doctrine. It's there's a notion of first order Boolean doctrine over any category with finite products. But just for this talk, to make it simpler, I'll take one specific category with finite products, which is fin set op. And this means that we restrict to the case where there is just one sort, as it's usual in the courses on mathematical logic, and no function symbols. This is a restriction to make things simpler to communicate. And okay, so a first order Boolean doctrine then is a functor from fin set to the category of Boolean algebras with some properties. I have a backup slide if you want to see the precise definition. But the property says that there are quantifiers, you can encode quantifiers, and they have the property that you want. And you should think of a first Boolean doctrine as arising in the following way. And actually, they all arise in this way. You take your favorite first order theory, and you associate to X the Boolean algebra of first order formulas, where you quotient the first order formulas with 3 variables in X, and you identify 2 formulas if T proves that they are equivalent. Okay, so P of X is this Boolean algebra, and P of morphism captures simultaneous substitutions. These are first order Boolean doctrines, and they are all of this form. And now Herbrand's theorem, to see it from a doctrinal perspective, it's useful to say that it describes the validity modulo universal theory. Well, not just for existential statements, but it can with a modest adaptation, you can do it for any formula of quantifier alternation depth at most 1. These are just bounded lattice combinations, so finite meets of finite joints of formulas of one of these form, either an existential formula or a universal formula. Okay, and Herbrand's theorem tells you when such a formula exists. Is provable from T. Okay, and the doctrinal reading is the following. Now you start with a Boolean doctrine, not first order, not necessarily first order, but Boolean doctrine, which means a functor from fin set to BA, just a functor. And in this case, this models the class of quantifier-free formulas of a universal theory T, where you identify 2 formulas if they are T interprovable. Okay, so just a functor encodes a universal theory, T, and the quantifier-free formulas of this theory. So the quantifier-free formulas modulo this theory. Now P has a quantifier completion, so there's a universal way to embed P into a first-order Boolean doctrines where we have all quantifiers. And as a subfunctor of this quantifier completion, you can easily define the functor of formulas of quantifier alternation depth at most 1, if you think this P as a quantifier-free formulas is these as all formulas. And Herbrand's theorem is an explicit description of P in terms of P1. Okay, just like in the usual statement, you reduce the validity of an existential formula to the validity of quantifier-free formulas. And this perspective we emphasize in this preprint with Francesca, where we provide a proof of Herbrand's theorem completely within the formalism of doctrines. And I also suggest this other recent preprint by Ridley on the same thing. So this doctrinal Herbrand theorem is a first description, the first step in the description of this quantifier completion. So this quantifier completion directly is difficult to express because there are many quantifiers that are nested, but one can hope to describe it layer by layer by progressively augmenting the complexity of the formulas you describe. So it's a first step in the description of 3 first-order Boolean doctrines via iterative addition of nested quantifiers. Good. And now I want to communicate my interest in the stone dual of Herbrand's theorem. And there are 3 reasons. One is an open problem by Pitts, which asked, okay, is every Heiting algebra the poset of subterminal objects of some topos? This is an open question. And Pattaya announced a positive solution using this technology, iterative addition of nested quantifiers and duality. However, he passed away before having left enough details, So this technology, now we want to start to develop it in the setting, in the simpler setting of classical first order logic. Second reason is actually what motivated us at the beginning, and we've been inspired by Margherite's talk at CT in Genoa, where she invited to push this doctrinal perspective together with a stratification of formulas by the complexity, together with duality. And in fact, much of what I'm presenting today, we took inspiration from a paper by Gerke together with Joyal and Reggio. And finally, there's a success case that keep us our hopes high, and it's that Ghilardi used iterative addition of nested implications and duality to describe free finitely generated Heiting algebras, for example, in proving some non-trivial fact, such as that all such free algebras are bi-Heiting algebras. And the criterion behind it is that dualities simplify these free constructions. Okay, but then let's see what is this stone dual of Herbrand theorem. Now, if you take a first order Boolean doctrine, so a functor from thing set to be A with certain properties, and we compose it with the stone duality, then we get a polyadic space. So this is the notion dual to first order Boolean doctrine, and it's a functor from thin set up to stone with a couple of properties. I have a slide with the precise properties if you want to know them, but these are correspond to the existence of a joint and the Beck-Chevalier. It's a notion going back to Joyal in a short abstract that I think he never developed, but just if you want to see some developments, I suggest some, for example, Marquez' PhD thesis or a paper of him with Van Hoorn. And it has a semantic polyadic spaces that have a really concrete meaning that they all arise in this way. You take a first order theory T, okay, since we are taking things set up in our relational language, and to a finite set X, you associate a certain quotient. So you take the space, the class of models of T pointed at X. What is it? Well, for X empty, it's just the models of your theory T, and then you take elementary equivalence. You quotient by elementary equivalence, where you identify two models if they satisfy the same first order formulas. In general, for an arbitrary finite set, you take a pointed model, meaning a model of T together with an assignment, an evaluation of the free variables, which just means a map from X, a function from X to M. And you identify here two models if they are elementary equivalent, meaning that they satisfy the same first order formulas with free variables in X. This is a stone space with a natural topology. And in general, this assignment can be turned into a polyadic space. And all of these polyadic spaces arise in this way. So they are really spaces of models. Okay, what we want to do for this stone dual of Herbrand theorem is the following. We start with a functor, just a functor, not necessarily a polyadic space. And this means that you should think of it as arising from a universal theory T, where you take the functor assigning to X the pointed model at X, modulo satisfaction of the same quantifier free formulas. So let's take an example. We take the empty language and the empty theory. In this case, E assigns to X. Well, what is a model pointed at X? It's a set together with a function from X to the set M. But then we have to identify two models if they satisfy the same quantifier free formulas. And there are not many quantifier free formulas here. They are just top and bottom, true and false. And so all models are the same. So this is the constant factor. Again, we are taking T as the empty theory. Okay, this has a dual, a first order Boolean doctrine is dual to it, and it's given by the quantifier free formulas. In this case, it constantly assigned to x top bottom. We know that it has a quantifier completion, and we have a description for this P1, the formulas with quantifier alternation depth at most 1. And dually, this quantifier completion corresponds to the models, modulo elementary equivalence. And between the two, you can find this E1, which are the models of T, where you identify two models if they satisfy the same formulas of quantifier alternation depth at most 1. Or equivalently, the same existential formulas, if you want, or equivalently, the same universal formulas. In this example, well, now how many classes of models there are? Well, now there are just 2 classes of models here, because there is the class of non-empty models and the class, let's see, for example, E1 of empty. How many models of T there are? Well, there is the class of non-empty models and the class of the empty model. There are 2 because they satisfy, one satisfies exist x true, which is a formula of quantifier alternation depth at most 1, and the other does not satisfy these, but instead satisfy not exist x true. Okay, and but now we want a direct construction of E1 in terms of E instead of doing this tour. So the stone dual of Herbrand's theorem will be a description of E1 in terms of E. And this is it. Now we don't do it in this talk. I will not describe the whole E1, but just to keep things simple, I will describe what is the value of this E1 on the empty set. So what are the models of T modulo satisfaction of the same quantifier free formulas of quantifier alternation depth at most 1. And this is the stone space of what we call Herbrand types for E. And here an Herbrand type is a subfunctor of E that maps finite products to quasi-products. So what does this mean? A quasi-product is means that the morphism to the product is epi. Here, in stone spaces, this means that it's surjective. Okay. Now, for example, here, this functor E has 2 Herbrand types. One is E itself, which corresponds to the non-empty model, and one is the functor that maps empty to the singleton, and any other set to the empty set. And this corresponds to the empty model. And now, what does this Herbrand type concretely means? Well, it means that we have a tuple of closed sets indexed by x infinite set, and it's this tuple is closed under substitution. If I take a disjoint union of finite sets, f of it is a quasi-product of the 2, And moreover, f of empty is quasi-terminal, that is non-empty. Under 2, this is equivalent to f of empty being a singleton. In terms of models, this means the following: that if we start with a universal theory, and I have the functor associated to it that maps x to the pointed modulo satisfaction of the same quantifier free formulas, then this Stone space of Herbrand types is homomorphic to the models of T modulo satisfaction of the same existential formulas, or equivalently formulas of quantified alternation depth at most 1. And this homomorphism is obtained by mapping M, the class of M, to the functor that associate to X, what you get if you consider all possible assignments, evaluation of X into M. You take the equivalence class, and then you take the topological closure. Yes. Okay. Good. So, for example, here, if I take the empty set, then if I take X non-empty, this set will be empty, because there's no way in which I can find a function from X to the empty set. And we've been inspired by a paper by Gerke, Joyal, and Rich on this. Okay, to sum up, the Stone-Joyal of Herbrand theorem is the following: given a functor E from thin set up to stone, we describe this E1, which is obtained by freely adding to E one layer of quantified alternation depth. Okay, we have a description for the whole E. Here I presented just for the whole E1. Here I presented just E1 on empty set, which is the Herbrand type for E. So the subfunctors which map fine products to quasi-products. Now, if you want to understand what is E1 of X, is defined similarly, and this works not just for thin set up, but actually for any category with finite products. And also with equality, you get the same construction, essentially because the quantifier completion works the same also when you have equality in the language. And that's all, thanks.